When your math is not, if you don't know how to apply things, I think you're going to land in a trouble. There's a wall actually, rigid wall. Some simple question is there. So he's asking find the speed of the both the bodies when the sphere hits the ground. How we can do this? Let me have water. How the wedge can move? I think we go back to laws of motion. The idea of laws of motion, I think, has to be taken care. And finally, the wedge will move like this, horizontal. And what about the sphere? Sphere will descend vertically. The sphere will just move vertically down and the wedge will move horizontally. And this is what happens when sphere landed. What was the sphere? Sphere will have velocity, say Vy. Wedge will have velocity Vx. What are the forces that are acting? Normal contact, N2, normal contact between the sphere and the wedge, normal contact on the ground, then the weight mg, here the weight mg. Can we apply conservation of mechanical energy? One more thing. What is the work done by N2? 0. Work done by Ng will be 0. Work done by this mg, weight of the wedge, will be 0. Work done by the weight of the space, non-zero. What about work done by normal? Non-zero. But what is the net work done by it? We'll see it. Okay, we have this one. So altogether, they'll be in contact, no? As long as the sphere is moving down, it'll be in contact with the wedge. So then n during the motion. So what is the first important condition? During the motion, the wedge and sphere will be in contact. So therefore n is non-zero. Work done by n, okay, will non-zero. So then go back to the basic constraint equation. If this is inclined plane, the displacement of wedge, let it be y. The displacement of the wedge, let it be x. That of the sphere, let it be y. How the normal contact will be acting here on the sphere in this direction, on the wedge like this. Net work done by normal contact, will see it. Net work done by normal contact, because before applying conservation of mechanics I had to go for it. Net work done by normal contact. Normal contact n sine theta does positive work on the wedge. Similarly, I'll resolve that n will be n cos theta into y does negative work on the sphere. Is it okay? Let's resolve this n cos theta. Then how x and y are related? X and y are displacement of block and wedge. Then as normal contact is non-zero, any constraint equation can you put it? X sine theta should be equal to y cos theta, because the displacement of sphere and the wedge along common normal must be equal. Reason for that? This is a condition. So what is the constraint equation? The displacement of sphere and wedge along common normal must be equal as n is not equal to 0 along common normal, because n is non-zero. There's a constant equation. So therefore now what is the constant equation? I can bring it, x sine theta equal to y cos theta. Now let me replace that here. N x sine theta, I can write it as y cos theta, n. So what is the net work done by normal contact system? 0. Then only force doing work is the gravity, the weight mg. So then I'll write it, decrease in potential energy of the, what is work done by n2? 0. What is work done by ng? 0. So only force doing work. Only force doing work is the weight of the sphere. So therefore decrease in potential energy. Now I can apply conservation of mechanical energy. Decrease in potential energy of sphere equal to increase in kinetic energy of sphere and wedge. So this will become mg2r should be equal to m vx square by 2 plus m. But we don't know vx and vy. Again, constant equation. You differentiate this, what do we get? Vx sine theta equal to Vy cos theta. Use these two equations and solve it. Okay, you see somewhere constant equation. See, take it for granted, whenever two contact surfaces are in contact, then their displacements or velocity or accelerations along common normal must be equal. Where all it comes, you try to apply it. This is what we learned from the laws of motion. You are studying work energy chapter. You are studying kinematics. You are studying